Greetings from the Black Hills of Dakota Territory, United States of America. Stan Jabalisco here with a conclusion, I guess, to a series of 4 videos having to do with calculations involving inductive and capacitive reactance. We have learned how to determine inductive and capacitive reactance values based on the frequency and the inductance or the capacitance. We've also learned how to determine a particular frequency or inductance value to attain a certain inductive reactance. So the purpose of this video, the subject matter of which is covered quite extensively in this book, Teach Yourself Electricity and Electronics, all editions. Current edition happens to be the 5th edition. What we're going to talk about here is how to determine a particular frequency or capacitance value when we want to obtain a specific amount of capacitive reactance. So let's get right to it. There is the formula for capacitive reactance, X sub C, in terms of the frequency and the capacitance. If we know the frequency in hertz and the capacitance in farads, then we can use this formula to determine the capacitive reactance in negative ohms, as it were. Remember, capacitive reactances are always negative. We will, for the purposes of this discussion, not worry about the J operator, but once again, you may wish to remember that J, the unit imaginary number, is equal to the positive square root of -1. And it's a mathematical method or scheme or invention that has been used by engineers to distinguish reactance from resistance when we want to talk about complete impedance values. But that's a little bit beyond the discussion right now. All we need to do is look at this formula. Now, we can use a little bit of algebra to translate this formula into this one. We simply swap the numerators and denominators and move the minus sign over to the other side of the equation. Then, when we take this equation right here and divide through by C and then flip it over again, we get this. The capacitance in farads equals 1 divided by minus the capacitive reactance in ohms times 2 pi, which I've memorized now after having talked about it so much, to 6 significant figures. It's 6.28318. That's 2 pi times F in hertz. Or we can also find the frequency in hertz based on the capacitive reactance in ohms times 2 pi times the capacitance in farads. These formulas will also work for capacitance in microfarads and for frequencies in megahertz, which is a lot more commonly used at radio frequency applications. So let's just suppose now that we want to obtain a capacitive reactance of, let's just say, minus 50 ohms. Now remember, we're talking here about capacitive reactance, so we need to put that minus sign in there. And once we do that, we can just forget about the signs entirely, because we're always going to have positive frequencies and positive capacitance values. So we can just say, we can just go with this, okay? So let's just get right to it. Just remember that the reactances always turn out negative. So let's just say, for the sake of argument here, 50 equals, now let's say that we have a frequency of, oh, I don't know, let's just make it 7 megahertz, just to be a little different. 7.00 megahertz, and we want 50.00 ohms, or pardon me, just 50.0 is good enough. So then what we have is 1 divided by minus the capacitive reactance, so minus a minus 50 is 50. Excuse me. Excuse me. We're looking to find the capacitance. Let's just start all over again here. You can just go right ahead and laugh at me, the old fuddy-duddy. I'm just going to leave this blooper right in here. We can take this capacitance, and that's what we want to find. We know the frequency. It's 7 megahertz, and we know the capacitive reactance is minus 50 ohms. So 1 divided by 50, remember minus a minus 50, 50.0 times 6.28318 times 7.00. So let's just bring our calculator out into here. Now remember, this is going to be microfarads. So let's just bring our calculator out. 50.0 times 6.283. Well, okay. I've had plenty of Diet Mountain Dew. I don't know what's going on here with this. 50.0 times 6.28318 times 7.00 equals 2199.113. Well, 2199.113. Let's just start over again. I sure wish this calculator had a reciprocal key. Maybe there's a trick we can use to make it do that. 0.000455. We'll round it off to 3 significant digits. 0.000455. 0.000455 microfarads. Well, remember now, if we move this decimal place over to the right 6 places, we'll get picofarads. That's probably a better way to write this. Remember, a picofarad equals 10 to the minus 12th farads equals 10 to the minus 6th microfarads. So that's how we can determine a capacitance. We want 50, or rather minus 50 ohms. I'm getting my signs confused. At least I came out with a positive capacitance. Minus 50 ohms of capacitive reactance at 7.00 megahertz. All right. Well, I think that you can probably manipulate this easily enough for yourself to figure out frequency, but let's just go right ahead anyway. And suppose that we have a capacitance of, oh, just for the sake of argument, 220 picofarads. And we want this inductive reactance to be minus 60 ohms. All right, so we'll just plug in those numbers. So let's do that. We're going to get frequency in megahertz now, remember. Equals 1 divided by minus a minus 60 times 6.28318 times the capacitance in microfarads. Well, 220 picofarads equals 0.000220 microfarads. So that's what we're going to use. 0.000220. So let's just plug those values right in here, and hopefully we'll get a little bit more luck here. 60. I don't really need to put the 0 there. Did I forget that before? 60.0 times 6.28318 times 0.000220 equals 0.0829 0.0829379. You always want to keep all of these extra digits in your calculation until you're done. Then you round off. You don't want to round off to 3 significant figures at intermediate stages. So, because you'll get what is called cumulative rounding errors. I believe I described that in the book. In any case, let's just say we've got 0. Let's start over here. 0.0829379. 1 divided by 0.0829379. And we're getting there. 12.05 megahertz. We'd round that off to 12.1 megahertz. So that's that. That's how you can do calculations like that. It's messy, it's tedious, and if you're better with a calculator than I am, heaven bless you. Stan Jabalisco from the Black Hills of Dakota Territory, United States of America, saying best regards and so long.